Let's start with a breathing exercise, if you are able. This is called box breathing. We'll breathe in, hold it, and then breathe out. Ready? Breathe in, 2, 3, 4, hold it, 2, 3, 4, and breathe out, 2, 3, 4. This is our most basic relationship with the atmosphere, the air around us. But for something we encounter every second of every day, it's not intuitive how it works. So in this video, we'll go more in depth into defining the atmosphere. We'll talk about what's in the atmosphere, its vertical structure, and then a little bit about local heating and cooling, or heating and cooling on a small scale. In our video about the Earth's spheres, I mentioned how the atmosphere is the air that surrounds the Earth, and that it contains the mixture of gases that support life. This mixture of gases mostly includes nitrogen at 78% and oxygen at 21%. This might be a little surprising since we humans really focus on oxygen because oxygen is the part of the air that we use for our biological processes like breathing. The air also contains about 1% of argon and a tiny percentage of other gases. The mixture of gases in the atmosphere stays mostly the same. There are some gases that vary in amount depending on local conditions. These include water vapor, so water in the form of a gas, which can range from 0 to 4% of the atmosphere. There's carbon dioxide, which we covered as a greenhouse gas. This goes up as fossil fuels are burned. And then a third important gas is ozone, which is mostly found in a specific layer of the atmosphere called the ozone layer, which we'll touch on in a moment. There are also other gases that vary in small quantities. And I'd also like to add that not all of the particles in the atmosphere are gases. We also have particulates or aerosols that are really small particles of solid matter. So these include ash and smoke, dust, pollen, and salt spray from the ocean. Okay, so now that we know a little bit about the contents of the atmosphere, let's talk about its structure. The atmosphere is composed of vertical layers stacked on top of each other, and these layers are distinguished by temperature patterns. We can see the temperature pattern by looking at that squiggly yellow line on the graph. When it moves left, temperature is going down, and when it moves to the right, the temperature is going up. We are in the troposphere here at the bottom. In this layer, temperatures go down as the altitude goes up. Altitude is the distance from sea level. So the heat source in this layer is the Earth. Recall how we talked about heat radiating from surfaces. So as we go higher, moving away from the Earth, it gets colder. The next layer is the stratosphere. This layer is different from the troposphere because the temperature actually starts to increase as we go higher in altitude. This is because the stratosphere contains its own heat source. It has this layer of ozone gas, which is a greenhouse gas that absorbs UV radiation from the sun, or ultraviolet radiation. As we go higher in the stratosphere, the temperature increases because more UV rays are hitting the ozone. And by the way, these are the same UV rays that cause sunburns and cancer if they reach your skin on the surface of the Earth. So we can thank the ozone layer for acting as our planetary sunblock. In the mesosphere, temperatures start to go down again with an increase in altitude. This is because the mesosphere doesn't come with its own heat source. Any heat here comes from the ozone layer in the stratosphere below it. And lastly, the thermosphere has temperatures going back up again. Molecules in this layer get hit with high energy radiation from the sun, like X-rays and extreme ultraviolet rays. But also, there is so little gas this high up in the atmosphere that the molecules are spread really far apart. When radiation from the sun hits those molecules, they're actually too far apart to share the energy between each other, so they just get really hot and split apart. The weirdest part about the thermosphere is if you were actually up there, it would still feel really cold because there just aren't enough molecules to even transfer heat to your skin. So these layers are something that we mostly teach in order to give context to the atmosphere. In reality, most of atmospheric science is studying the troposphere, that first layer where we live. And now that we have the composition and structure for context, let's turn back to the basics of air movement back in the troposphere. Because air isn't something we can really see that well, in atmospheric science, we use air parcels. These are imaginary bubbles of air that we can follow around as they move. Separating parcels out like this is helpful as a teaching tool. You can imagine the parcel as something like a classroom size or a building size. So let's see what it does as it heats up. Some of you may be familiar with the phrase warm air rises. We can feel this, for example, if you stand on a chair in a room with a furnace. The air at the top of the room will usually be warmer than the air below because warm air rises. When air rises, it starts to expand because there's less air on top of it to keep it compressed or squished. When it expands, it cools. And without getting into too much physics, this expansion causes the gas molecules in the parcel to move less rapidly because they have more room. And this means that the air cools down. So when we have an example of matter like air cooling because of a decrease in pressure or less squishing, we call it adiabatic cooling. That means the temperature is going down even though no heat is leaving that system. It's all because the parcel is expanding from less pressure. And the opposite effect is also true. Cold air sinks, compresses, and then warms. So that's how air moves as a parcel, this imaginary, idealized version of air. And now that we have the basics of rising and sinking, we can talk a little bit more about air pressure and its relationship with movement. But rather than focusing on an air parcel, I think it's easier to visualize with a more realistic scenario. So let's talk about wind, and more specifically about sea breezes. Wind is natural horizontal air movement, and it's often caused by uneven heating. You may recall from a few weeks ago that uneven heating by the sun causes the seasons. Well, it also causes air to move around. So let's watch what happens along our coast here. After sunrise, sunlight starts to hit the Earth's surface. And because the ocean is able to mix heat around better than the land can, the land surface will heat up faster. This also heats the air over the land, and the air rises, just like an air parcel. This air builds up aloft, meaning higher up, and this causes high pressure because it's all squishing together up there. It also causes low pressure at the surface because air is missing down there. Compared to this high pressure zone over the land, the air over the sea is relatively low pressure. This causes air to be drawn away from land because air always wants to go away from a high pressure zone. It is basically being pushed out by the other air. When air is hanging out over the ocean, it'll start to cool and then sink. And this causes another high pressure zone, this time over the ocean's surface, because air is just piling on top of it. And then by the afternoon, this causes that surface air to flow back to the land, which we experience as a sea breeze. And we call this convection, a cycle of air rising, flowing horizontally, sinking, and flowing again, which we feel as wind. And in case you don't live on the coast side, it is possible to experience this phenomenon with smaller bodies of water. I used to live in San Jose, and the wind coming off of the bay on summer afternoons could get pretty crazy. So this video took us through the composition and structure of the atmosphere, and then some basics about heating, cooling, and the movement of air. Next time, we'll be scaling up. We're going to go from local winds like sea breezes to global circulation, or the patterns of airflow on a planetary scale. Thank you for watching, and I'll see you next time.